So welcome to the new AI4OPT series, and so we're excited to get started with the new semester the series and Bastani. So Hamza is a faculty member in the operations at Wharton School at UPenn, and she works on machine learning algorithms for data-driven decision making with applications in healthcare, social good, and renewable. And Hamza has received several awards, including the Wagner Prize for Excellence in Practice, Scala Award for Best Paper in Healthcare, and she received the Best Award 3 times, 2016, 19, and 2021. And Behavioral OM Best Paper Award, and first place in health and hands-on story. So today she's going to talk to us about learning for global health supply chains. So without any further delay,
thanks so much, Siva, and thank you guys for having me here. Is this too loud? It's okay. So this is very much a work in progress. So I'm really looking forward to getting any feedback. I think I'm already loud, so I'm gonna. Is this okay? So I'd love to get your feedback and keep this as interactive as possible. Maybe I'll turn this towards me. Is that better? Okay, great. So again, thank you guys for having me. Would love to get any questions, so please interrupt me. So this is joint work with a bunch of people that I should acknowledge. So first of all, we're working with the Sierra Leone National Medical Supplies Agency. That's actually where this project started, on trying to better distribute essential medicines amongst different health facilities in the country. I actually got involved through this because of Macrorize, where I'm a technical advisor. So they're a company that uses AI to improve global health supply chains. And then finally, of course, collaborators at Penn. So Angel over there is my PhD student, first year at OID, and then Bastani is at Penn Computer Science. So most of the decision we're learning the technical stuff is doing work with Osbert, Angel, and Sahid at Macrorize, but then we're also working with a broader set of people from Macrorize and National Medical Supplies Agency to actually deploy this, which is currently in progress. So the rough problem is kind of pretty simple and straightforward, something you've probably seen a lot in your own work. So basically, Sierra Leone is one of the most impoverished countries in the world, and they have the task of distributing a limited inventory of over 100 different essential medicines across a number of health facilities. So these points here are actually different types of different health facilities throughout the country, and they're actually colored by type. So some of them will be hospitals, some of them will be district medical stores, and so on. But all of them kind of dispense most of these essential medicines. So we want to kind of basically match supply and demand. But the big problem they face is that demand is actually highly uncertain. So if it was fairly stable, this would be a really easy problem. But there's a lot of seasonality effects. There's a lot of cross correlations across different types of medical products. And so the uncertainty, the demand patterns basically look very, very spiky. Couple that with very, very limited budgets. So often a lot of their budgets are coming from USAID or other kinds of donor foundations. And so it varies a lot year to year. It actually means that often we don't meet the demand. And on top of that, we actually overstock in places where we don't need to supply, and we understock in places where we do need to supply. And that's a problem because, you know, the infrastructure is not great, so it's not easy to kind of fix that in real time. So 42% of their essential medicine needs are currently not being fulfilled across some of the focal key medicines. And so the goal at a high level is kind of, can we use, you know, techniques from AI and OR to do better than their current approach? So let me very briefly tell you what they do right now. So health facilities basically put in a request. So it's not really a request because it's more of a 3-month rolling average of their demand. This is a little bit problematic because there's actually a lot of missing values in the demand. And so the rolling average might be undefined, and how they impute it causes various issues. But this is what they're doing roughly now. And they have a very, very complex Excel-based allocation tool. So this is a screenshot. This is actually very, very common in global health. So if you work with WHO or other organizations, they built like population-based targeting, and then they'll have poverty modifiers, facility level like prioritizations. And so there's a lot of ad hoc rules that are lumped in here. And then after they implemented the original allocation tool over the years, policymakers at Sierra Leone National Medical Supplies Agency added more prioritizations. And so this thing kind of became very quickly a mess. And if you've ever worked with Excel tools in policy, they often have bugs. So while we were re-implementing this in Python, Angel actually found that one of the columns it was referencing was the wrong column. And so, this kind of does not do well for a number of reasons beyond just the policy design itself. And roughly what they do is so here's National Medical Supplies Agency in Freetown, which is the capital of Sierra Leone. This is kind of the richest, safest area, if you will. And then as you go north and stuff, you see more impoverished, more health inequities and so on. And so you get these stock, all the full stock comes to NMSA, and then they basically have to decide how much they're going to distribute between medical stores, district hospitals, and Western hospitals. So that's that facility type based prioritization. And then they actually just send it out in different stages. So there's about 1,200 local facilities for medical stores, there's fewer hospitals. And so this is a fairly complex layered process, which, introduces a lot of inefficiencies. And so what they were really interested in was an end-to-end solution. Any questions about current approach or the setting? Great. So how does it work? Like I mentioned, so we're going to focus on 8 focal essential medicine products out of the 100 plus, just because they have kind of cleaner data, and also they capture a variety of different demand patterns. So right now we're trying to expand to the other medicines, but this is what we've looked at so far. So amoxicillin, for example, is a very popular antibiotic. And there's different kinds of medicines. So things like magnesium sulfate, this is largely for pregnancy-related issues. And so it has very, very erratic demand patterns. And so it's very, very hard to predict. Even with machine learning, it's very hard to predict for magnesium sulfate. So you can see that there's a lot more unmet demand requests there. Products like amoxicillin are more smooth. And so it's kind of easier to, meet the to minimize unmet demand. But this is how the current allocation process works in a given time period. So now I want to jump into trying to figure out what an end-to-end solution would look like here. So a very popular framework that's useful and accessible for practitioners is what people call predict and optimize. So in the first step, you basically train a demand prediction model for every facility and product. So I want to know how much of demand I'm actually going to see for amoxicillin next quarter at this particular facility. And then once I get those point predictions, in step 2, I can actually optimize my allocations based on those predictions, right? So that's like a simple first step kind of solution. But of course, this is not very efficient because it's not really end-to-end, right? In step 1, we're not really accounting for the fact when we're building these predictions that we're actually going to do an optimization downstream. So there's actually an active area of research on end-to-end learning. So there's been a lot of work kind of looking at kind of this setting. And a lot of different approaches have been proposed. I'm going to focus on the subset of research that thinks about how we can do step 1 better, accounting for the fact that step 2 occurs downstream. So that's what we call decision-aware machine learning, because we want to build our predictions in a way that's aware of the downstream decision. So let me just give a little bit of notation here. So the goal with learning and optimization is given some response variable y. So let's say that's today's demand. I want to compute a decision z. So that might be my inventory that I want to allocate. And we want to minimize a known decision loss L. So z star of y, the optimal decision is going to minimize L of z given some demand y. Of course, in practice, y is not known, right? So demand is unknown. So what do we want to do? We want to predict y based on some covariates. So in this case, it might be lagged demands from that same facility for other products, this product, whatever. This step can actually be extremely complex. So modern data science pipelines are very, very complicated. And so we want to try to keep this part as general as possible in order to get like the full power of machine learning. So in the training phase, we now minimize a different loss. So now note that the decision loss was L. I'm going to call this L tilde. So in the training phase, we've given you historical examples with features X and response variable Y. We want to train some arbitrary function F theta to predict Y. So this could be a neural net, random forest, some more complicated meta learning pipeline. And so here I'm going to use L tilde. And the testing phase basically says, given a new X, I'm going to form a prediction. So I predict demand, and then I choose a decision Z star. So I optimize my inventory given that predicted demand, right? So the question becomes, what loss L tilde should I use when I'm training my predictive model? So if you talk to any practitioner, they're probably using scikit-learn or TensorFlow or something. So they're probably using what I'm going to call decision blind prediction loss. So they're just minimizing mean squared error, right? This is what most people do. You build a random forest model, minimizes mean squared error, and then I plug it in wherever I need to plug it in. If you wanted to do instead a decision aware prediction loss, the ideal loss that I would use is actually the objective of the optimization problem I'm solving, right? So now I'm going to bring in L tilde, I'm going to write out L, so it's the actual decision loss L, given, Z star, which is the optimal thing I would have chosen, given your point prediction Y hat, which is actually a complicated thing because Z star itself is the minimizer of L, the decision loss, right? So this is a fairly complicated object that's not, really computationally tractable. Questions about? Okay, so how do I compute L tilde? Well, in general, I can. So here we're going to think about trying to approximate L tilde so that we can do better. So some properties that we could be interested in. There's a lot of approximations of L tilde. So let me just say, what we want to do is, first of all, we want it to be general. So a lot of prediction problems, in order for them to be effective, you actually want to build. So for example, in the Sierra Leone case, we found that we had a meta learning random forest model that was able to kind of predict across product and across health facilities. So we want to keep as nice as possible. And we also, the optimization problem in general might be nonlinear and kind of messy. So we'd like, to allow for an expressive class here. We, of course, want it to be computationally tractable, right? That's important for it to actually finish running. And then finally, we'd like it to be principled in the sense that it actually approximates the optimal decision class. So these are some properties, right? So let me briefly talk about some prior work. So one is, I think one of the earliest work in this area is probably like Dimitri Bertinas and Nathan Pallet had some work on basically what they do is they cluster nearby observations using CART or LOES to estimate a conditional distribution Y given X. So you want a feature-based heterogeneous conditional distribution. And then we plug it into, SAA or some sort of stochastic optimization approach. And so this was great. It was like the first step towards doing this the right way. Here, one issue that I would point out is that the predictive model, we're not retraining the predictive model is based on the optimization problem that we're solving. And so it's not optimal in the sense that it's not approximating the decision loss and accounting for that when you're training the model. And also it's not computationally tractable for more complicated predictive models. So Nathan actually went ahead and wrote a second paper to kind of address the second point. So they actually built out with his student Xiao Jimao a specialized approach for doing random forest plus sample average approximation. And so this has a very specialized way in forming the tree splits when you're building your random forest that accounts for a specific optimization structure. The reason I'm emphasizing that is because it actually doesn't work in our meta learning setting. So they actually need one unknown parameter vector per optimization problem. And we'll see that in kind of a more meta learning approach, you induce these correlations that it doesn't work with. And the other issue that we ran into was that it wasn't computationally tractable. So every tree split actually required resolving the optimization problem, which, in a random forest, you have hundreds of trees and there are many, many splits. And so this quickly got out of hand. So it works for like a single news vendor or something like that, but not when you're solving across 1,000+ health facilities and 100+ essential medicine. Okay, so the paper that we really drew inspiration from was Adam Elmer-Suba and Paul Riggers' paper, which basically was where we learned about directly approximating L tilde, right? So this one is very specific to LB and LP and the prediction function being linear, but we're going to take a very similar approach. And so the only issue with this, it is principled, but the only issue with this is that the strategy is very specific to linear models and kind of having known constraints. So we'll have uncertainty in the constraints as well. So we're just going to try to generalize this approach. And then finally, there's some excellent work by Brian Wilder and others on back propagating through the decision loss. So this one also has this has two issues. One is that it doesn't work with our meta learning setting because it's one optimization parameter per instance. The prediction function also has to be differentiable so that you can backpropagate, which doesn't work for random forest. And it's also less computationally tractable. It is more computationally tractable than some of the other approaches, but you still have to solve the optimization problem in every gradient step. So we're going to try to do something that only solves the optimization problem at most points. Questions here? Great. Okay, so what are we going to do? We're actually going to do something really simple, which is we're going to tailor extend y hat around y star. Why? If you're building a high performing predictive model, you hope that your predictions are kind of close to the true parameter that you're predicting, right? And so if you believe that you're in that regime, then you can tailor extend around that. And what you get that this is the optimal decision loss. So the first term here is just L of B star Y star. So this is a constant, right? Because it's not actually, I mean, it's regardless of performance, so you can ignore that. And so then we look at the first order term. The first order term is 0, then you look at the second order, right? So the first order term, the coefficients are basically a product of two gradients. The pink one is the effect of the decision on the decision loss. So how does V affect L? And then the yellow part is the effect of the prediction on the decision. So how does Y, like my estimate of the demand, affect how I want to allocate my inventory? So this is very simple. It basically decomposes into these two gradients, which we can compute, right? So if we were actually going to then change our prediction objective, so instead of minimizing mean squared error or trying to minimize the crazy decision loss, we might consider just minimizing that first order. So again, if that's 0, you want to take the second order term. And so it would just be this, right? So it's just, and now what's nice about this is it basically looks like a regular loss because f theta minus y star is just the difference or the difference in your predictions. And so this basically looks like a reweighting of my samples, right? So these coefficients are actually constant in theta, the parameter that I'm trying to recover. And so these basically translate to weights on different training data instances. So all I'm saying is that some training data instances are more relevant to the decision loss, whereas typically in a decision blind prediction, you would treat all training instances the same. Right? Why is this great? It means that if you have an existing training package that you're using in scikit-learn or TensorFlow, you don't need to actually retrain the package. Like you don't need to build a new package or use it. You can simply enter a set of weights, which is very powerful in my opinion, because I've never been able to convince any practitioner to like use a new package that they're not familiar with and it doesn't come with the same bells and whistles. Okay, so how do you compute these gradients? You need to compute the gradient through the optimization objective and the optimization decision. There's actually some really nice work by Brandon Amos and Zico Folker on how to do this efficiently numerically. So in general, you won't be able to compute it analytically. For the Sierra Leone example, for a kind of a bare bones stochastic optimization problem, I'll show you what it looks like analytically. But in general, you would just compute it numerically. Questions? Yes. On this what? Yes. Being able to compute numerically the grade. Yeah, so in our case, either you need to compute it analytically or you. Yeah, that's right.
So you mentioned the work with analytics.
Yes.
So that
Yeah.
So what is actually a range of our.
So here I'll show you. Do I have the? So in our case, the biggest constraint is not. The biggest constraint is that we have uncertainty in the constraints. So basically, like unmet demand, if you're minimizing unmet demand, it's the minimum of the demand that you're getting first. And so what we linearize it in the usual way, where it's like some parameter that you put in the constraints, and so the demand will fall into the constraint, right? And then you can't use their approach anymore. It's very specific to linearity perspective. Whereas here, like, so this gradient is supposed to be 0, right? The partial of V. The reason it's not 0 is because it's not an interior solution. So we actually need the fact that these constraints are binding. I mean, it's not you solve the second order term, and then it's not linear. So either way, it's different. Yes. Right. Yeah, yeah. So this is just basically it reduces to having a reweighting on your training data. And we wanted to make it look as similar as possible to decision blind loss minimization. But you'll see the reweighting of the data points is actually like pretty critical. And the reason that happens is because imagine that you have a function that's like, you're always fitting a misspecified function, right? But some of your training data is sort of more relevant to the decision loss, right? Like things that are near the decision boundary. And so what this is basically saying is let's focus on the training data that's like near the decision boundary. And I'll show you a very simple, intuitive example for the inventory case. Yeah.
Loss is either norm square or norm.
Yeah, this one's weird, right?
No, absolutely.
Yeah, so this one's weird. So I'll show you later that once you compute the gradients, you can upper bound this by like the absolute value, and then we do a mean absolute error. Yeah, or you can go to the if it's not the case, you can go to the second order, which looks very similar. It's just messier. Yeah, exactly. That's a great point. Cool. So how would you actually operationalize this? Well, in step one, you train an arbitrary decision line model F data. And then you compute your gradients through some optimization problem to obtain the training data weights W. And then once we do that, we retrain the predictive model with the weighted training data. And then we run the optimization problem again with these plugin estimates. So we're gonna basically, computationally speaking, we're running the predictive model twice. Are we training the predictive model twice? And then we're running the optimization problem twice, right? So much less effort than typically needed. And we think this is like fairly general because it only requires reweighting, especially in terms of the data science pipeline, because it only requires reweighting the observation. So if you're doing some complicated like meta learning thing or transfer learning thing, this is like very easy to incorporate because all we're gonna do is supply those weights. And you can use any off-the-shelf machine learning package. There's no re-implementation that you need to do. It's tractable because, like I said, you only have to do the predictive model training twice and the optimization problem twice. And it does directly approximate the optimal decision loss. So same thing that Adam's doing, but in like a more general. Okay, so are there any questions before I jump to giving a concrete example? Yes. So when you're training the model, you have Y star, right? So it's not for the test set. And then we just use it for the test set, we just use the plugin estimator of F data. So it is true that you could go back and forth if you wanted to, like almost like an EM or something. We didn't empirically see any value to do that. Yes, yeah. At first I was like, oh, we should just go back and forth. But then at least for the problems that we've tried, we haven't seen any value for doing that. And I'll show you why. It's actually like a very simple. So for the essential meds, like the 8 product, we're going to focus on 8 focal products. So one is for child health, like very young children, maternal health, and then family planning. So these are the 8 that the policymakers kind of picked up for us to start out with. And then, like I said, right now we're trying to move on to the 100. And so the data is basically, we source data from DHIS2 forms. So anyone who's worked on global health, this is sort of the classic form. They use it in a bunch of other African countries. And so we have data. The Sierra Leone was kind of late to the boat. And so they kind of started using this in January 2019. So we only have about 31 months of information, if you will. And a big challenge is that there's a significant number of missing or unreliable values, right? So this is the time series of the number of missing or unreliable values. You see in the beginning, it was actually like close to 100%, so there's like no data. Then the policymakers started yelling at them, and so it started monotonically decreasing, and then it kind of plateaued when there was COVID and a bunch of other things that they needed to deal with. And so a big challenge here is going to be like how to kind of get around that. So that's like a standard machine learning problem. Sorry. I feel it. And so what does this become? Basically, we have 9,000 separate time series, right? So why 9,000? We have about 1,000-ish facilities, more than that. And then we have each product. So each product will have its own time series for each facility. And each of them only has about 18 observations on average, right? Because there's a lot of missing values. So if you do like kind of standard time series forecasting, that's going to fall short. Oh, sorry. Thanks. If you do standard time series forecasting, that's going to fall short because, you know, we only have 18 observations, right? So what you really need to do in this setting is try to do some kind of cross learning across products and across facilities, right? So what is the idea of meta learning? Basically, like I have a time series for demand for a particular hospital and a particular product. It's very little data, but then I can say, oh, but I have a bunch of different facilities for the same product, and so I can use that information. And not only that, but at this facility, I also have a bunch of different products, and so I want to kind of learn across them, right? And if you actually try, you don't want to make them actually equal to each other because each facility and each product has its own kind of classic characteristic pattern, but to the extent that we can, we want to minimize variance. And so this basically is like classic bias variance trade-off. If we just train on the data that we actually have, we're going to have very, very high variance, but we'll have low bias. This is if we had a linear model. And then if we actually train on the proxy data, then we end up having very little variance because we have all of the data across locations, but then we end up getting a lot of bias. And the whole idea of meta learning is, can we do better than this by, you know, tuning this bias variance trade-off. Right. And so what we did is we've actually done, my group has done a bunch of work on this. We're using using data from other facilities or products as proxy data. And so in this case, we ended up using a random forest like meta model with jointly forecasts across all 8 products in 1,200 time series. I won't go too much into the details, but there's a decent amount of hand engineering to actually get this to work, right? And so there's very little flexibility in kind of the machine learning pipeline. If not, you kind of just get lost. Okay, so these are out of sample results for a decision blind random forest. So as you saw in our pipeline, we basically have to train the model first before we can try aligning it. And so these were results we actually presented to the for each of the products. We see in pink kind of the 3-month rolling average forecasting error that they're using, compared to the green bar, which is like our random forest approach. And then the yellow is kind of capturing the improvement. So you can see that on average, we're getting like 34 to 59% better demand forecasts on a held out test set month. So we look at March 2021 and we'll say, okay, we're not going to use the demand data. Let me use my predictions. And we actually do better, right? So that was great. So now we want to actually align this with some sort of optimization problem for doing the distribution, right? And so this is going to be like a very bare bone stochastic optimization problem because a lot of parameters that you might want to include are kind of unavailable. So this is just what we're starting with. So the goal here is to allocate AN star across N districts that minimize cost, and facilities that should be. My objective is going to be the cost of unmet demand at each location. So this is what I meant by it's like not really linear. So I have basically EN is my demand. SN is my inventory, and AN is kind of the allocation that I'm providing them. And right now, I'm just going to assume that unmet demand at any location is kind of equivalent. So if I don't give Swati something and I don't give Siva something, I'm going to treat that as the same. And we're working on kind of trying to adapt that to hospitals versus medical stores, but this is the preliminary model, right? And then we have constraints, like we have a fixed budget B. So this is always going to be a binding constraint in our case, which is how much we can actually distribute. And each facility can hold more than its current capacity. So this is especially important for medicines and also vaccines, which we've been working on because they're very stringent, like refrigeration capacity, for example. Did I do something weird again? Sorry. No. After all this time, I should really know what to do. And so we're going to do stochastic optimization. We're just doing sample average approximation. So obviously there's a lot of uncertainty in these predicted demands. So we're going to draw random demands at each facility based on the estimated distribution. In a random forest, how do you get the distribution? We just look at the tree distribution. So we have about 500 trees. We just draw from one of those trees. right? And so we know all that of this can be solved very efficiently as a linear program with SKA, right? So this is the problem that we want to align our predictions to. And so one issue that you'll see with this particular prediction problem, optimization problem that we've written down, which I would say is probably not normally the case, is that there's a lot of degeneracy in the optimal solution. Because if I'm understocked, it doesn't matter where I'm understocked. And so there's actually like a whole bunch of solutions. And so the gradients are not like super well defined. And so to get around this, what we did was we basically perturbed the demand a little bit with like some Gaussian noise. This is just to compute the gradient. And then after that, we take sigma to 0. So that noise will take to 0. This is just so that we can compute the gradients. Which time do I have? Okay, great, thanks. And so you can do this in like a kind of standard way. So this is the LP solutions gradient. If you recall, there are actually 2 gradients that we need to compute. So you just write down the Lagrangian, and then it's kind of a mess. You write down the first order condition. So the weird thing that shows up here is because we have the degeneracy eta, the distribution of the normal noise that we're adding to the demand distribution actually shows up, which normally wouldn't show up. Yes. We did, and then we got worse allocations, at least when we were showing it to the policymakers. So it's very dope. So yeah, when we first looked at this, we were like, we should do C-bar or something smarter. This is kind of what looked best to them, and so that's why we went with it. And you'll see that this will actually give you something really cute and interpretable in terms of the gradient and the weighting. So I prefer it on the slides also. Yeah, so it's messier at first, but it'll be cleaner later. And then if we take the gradient, you get this kind of like approximate gradient. You get this 1 over n term because of the CF, but you can ignore that. Basically, it just becomes a delta function. And then the second gradient also simplifies nicely. It becomes an indicator function of whether or not my inventory plus the allocation is less than or equal to the demand. So basically, like, am I understocked or overstocked? So when you put this all together, this is what the weight is, right? So the weighting, this is the approximate predictive model objective. The weighting is simply whether I'm understocked or not, right? My demand exceeds my current inventory plus whatever allocation I'm given. So this is very simple and interpretable. What it's saying is that I have lots of health facilities. I don't really care about the overstock ones, right? For those, I don't really need to get that demand exactly correct. Like, it doesn't matter if I'm off by a bit. But for these understocked facilities, it really matters whether I'm off by a bit, because that's actually changing how much I'm allocating, how much inventory I'm giving them. So some of these hospitals, for example, they might have lots of storage space, they might have lots of existing inventory. For them, it's not a big deal. I don't need to weight them in my demand prediction. But when I'm thinking about those like Western urban hospitals that are maybe impoverished and have like less shelf space and stuff, those are the places where I really need to nail the demand prediction, because I'm trying to basically send them exactly what they need or something close to that, right? And so that is the problem with kind of just doing a decision blend prediction. So even if we have a very high functioning predictive model in classic machine learning, it spends a lot of its capacity on kind of treating all of the samples equally. It's very democratic in that sense. But if you're looking at a downstream optimization problem, an actually worse predictive model might do better, because it's better specified in the region of the decision boundary, which is the only thing we care about for looking at the decision model. Does that make sense? Any thoughts? Cool. So now I'll show you some out of sample results. So this is on these 8 essential medicines, again, looking at the same thing. Here I'm going to compare to a decision aware approach versus a decision blind. So the same meta learning random forest approach, but the pink bar is the decision aware approach on the unmet demand. So of course the decision aware model is actually going to be worse prediction error wise, but we're looking at the objective, right? And decision blind, again, is course, and you can see that it actually helps a lot for most of the products. It doesn't help it for magnesium sulfate, because it's hard to predict on magnesium sulfate. They have very, very erratic demand patterns. And so if you can't even figure out what the prediction is, like how do you figure out what the weights are? So it only helps a little bit. But for some of these other products, it kind of helps a lot. And then we also, just for some external validity, tried doing this on vaccines. And so we were looking at 3 vaccines, BCG, measles, and pentavalent. And you can see that it helps here too. It helps a little bit less. Again, I think because for vaccines, the opposite problem, the demand is kind of somewhat more stable. And so you don't need to worry too much about it. But again, you see like kind of improvements across the board. And again, all of these 2 models are the same. They're both applying kind of our stochastic optimization problem with the random forest plugin for demand. Right? We're not comparing yet to the actual allocation tool that they use. So let me show you, now going back to what Sierra Leone was doing. So again, they were getting about a 42% unmet demand. This comparison is, I don't like showing this comparison because it's a little bit unfair because their allocation tool is kind of a mess. So this is really not like what I'm going to show you is not the value of our approach necessarily. That was a previous slide. It's the value of kind of looking at the data and building optimization into it, right? But this is roughly what you get by essential medicine. So this is unmet demand. The green bars are unmet demand using kind of what they're doing right now. And the blue bar is unmet demand if you were to use, kind of all of the data-driven tools that we talked about. And so it seems like there's actually really promising end-to-end improvements that you can get over the current system by just using, this combination of AI and optimization and basically just looking at your demand, right? So it looks like you can actually reduce for some products a huge amount of unmet demand for focal essential medicines. It's actually this improvement degrades a lot for like the tail end of the essential medicines because there the data is much messier. And so these expert crafted allocation tools are not bad. For these 8, it's quite bad, which makes sense, right? So these are the better data products. Any questions? Great. So we also looked at this by district, and we see the same thing. So it's not like we're screwing over some districts to basically, help other districts. Like in the improvements are kind of spread equitably, which is of course something they care a lot about. So now we're moving on to actually trying to deploy this. And one of the advantages of using something like the HIS2 data is that it's actually shared by a lot of other countries. So like Macro is operating our test coverage, Mozambique, DRC, and so on. So we're trying to get these sorts of dashboards in place for them so that they can actually do these allocations. So this is an example of what the current demo dashboard looks like. So basically you have a map, you have this AI predicted demand forecast, and then we have some suggested allocations based on that. Policymakers love maps. So this is obviously much prettier to look at than the Excel allocation tool. So, usage varies on a lot of factors that are not necessarily just performance. But I think there's a lot of exciting questions that I think we just kind of scratched the surface. So one of the things that we're really excited about is there's a lot of missing data, like we mentioned. And so one of the things that you might think about is how can we go and collect some of this information to build my predictive model, right? So far we've assumed what's missing is missing, but actually you can hire an RA or someone to actually go and call health facilities and ask them, what was your demand last quarter for this particular product? And if you're doing that, obviously you can't get all of the missing information. You have some limited budget. And so you might think about how do you actually target collecting missing information in a way that's like most likely to improve your decision-aware learning model, right? So the fact that we want to focus on locations that are actually relevant to our optimization loss means that you might want to think of this differently than kind of the classical Shapley values that people have looked at in machine learning to measure value of data. And also one of the things we're thinking about is how to do this for a more forward-looking approach. So this approach, this Taylor expansion, actually works for any offline reinforcement learning problem, as long as your feedback is exogenous, which is the case here because your demand is exogenous compared to your inventory decisions, at least the first quarter. But one of the things that you might think about is what happens when that's not the case, when your actions actually affect kind of future demand realizations. Then in general, we need to figure out like how this would actually extend. we're also interested, these demand forecasts are actually used for a lot of other downstream decisions by policymakers in these countries. So for example, like the current one is actually used by a company called M-Pharma, which makes other like pharma inventory decisions that are actually sold. So these are like free essential medicines, but they're actually things that you need to sell as well. And so we don't always control what decisions they're making, right? Even in a tech company, like usually the team that's building the predictive model and the team that's using the predictive model for whatever optimization problem, they're separate. So if you only add a prior on your decisions as opposed to actually knowing what they are, you might act differently. And then finally, I think there's a huge human AI interface question here, which I have no idea how to tackle, which is that ultimately we give people these allocations and then they actually go to do them. And then it turns out that, some of the trucks did not arrive or some road is down. And so they actually can't implement the allocation that you've actually suggested that they implement. And so what do? They kind of take this extra stuff and then they go around looking for the first empty truck and they put it in there, right? Which is not optimal. Like it kind of underlies anything that we're trying to do. But then, you can't expect a policymaker to then go and, formalize this new constraint that they've just seen happen and plug it into your constraint optimization problem, right? That's not possible either. So what we're trying to understand is, if we have some new constraint that pops up, is there any way that we can interpret the solution of the optimization problem in a simple way so that they can understand if there is excess inventory that they can't send to a particular location, what is the place that they should prioritize sending it to? So not the first empty truck, but maybe the first empty truck that's going to this particular district, right? So we haven't even scratched the surface of this, but I feel like if you work on any kind of policy problem or resource constraint problem, this always shows up that there's auxiliary changes to the problem that show up at the time of implementation, which you didn't have information about prior to that. And that is it for me. Thank you, guys. This is going to work with a bunch of people. So that's Oscar and Angel, Bekita and Yona, Musa, Ashley are all on macroize. Musa and Ashley are deployment managers, so they're the ones doing the dashboards and everything. And that's Dr. Lawrence and is head of PMs. Yes. So you have when you're doing that Taylor expansion, you can go to the second order. So so basically, if you have an interior solution, for instance, which we never have because we have a stringent resource constraint, then you can actually compute that. But that's only if you're, for our case, the first order term is non-zero, so I didn't put it up there. Yeah. When there's excess demand? So we never actually give the product to a facility unless we think they might need it. Because it's always better to store it in the central location than to have it stuck in some facility where it might get lost. But right, so there's the general problem and our specific problem. For a general problem, if you think that for some reason you have an interior solution, then yeah, when you compute these gradients, you can tell that some of them will be zero. Right, right. So one thing that actually happens if you don't model is this pooling thing. So like if someone shows up and there's no product, then they can go to like a nearby health facility. That's like to first order very difficult because of infrastructure issues and like a lot of these are maternal things, so they can't. And it's not transportation is not easy, but it definitely happens. We just can't quantify it, so it's hard to put in the model. But it's right. But then it has to happen locally. So like if I have unmet demand here and extra supply here, which it happens, but I don't, my understanding from on the ground is that it's not.
true that they have to be less. So because you went through all those calculations to essentially show that the radius has small.
Right.
We basically also going to do that.
Yeah, let me get back here. Sorry. Yeah. Right. Right. I don't think that was very clear, but like is for like a fairly not here. I don't think you can deal with on. I think that like the first time. So I meant more general than but not general. Yeah. Sorry, it's longer than I remember it being. This one. Yeah. That's where that complicated. If you still a grind game, you take the first order conditions and then we solve it. It's basically your standard ML 101. Not the budget. So for magnesium sulfate is where we had a lot of problems, and it's not that the budget is the issue, it's more that the random forest is not as good. So like the 3-month rolling demand app is actually like okay, right? So when is the random forest good? When you have like predictable demand functions that you can learn with like limited data sets, right? And so where we're really struggling, like at tail end of products, you have like maybe sometimes only like 2 observations, you can't do anything. And so then, you know, like there's no value in doing something smart. The budget, yeah, I think we could figure out, I think you have a good point that if we could figure out which budgets are most sensitive, probably that's useful for like US8 or something, you know. But they're also interested in kind of this like, they're interested in a lot of things, right? It's a complicated thing. So they want to like maximize benefit. They also want to get rid of their expenses. So we haven't even touched that part. We're taking it as exogenous, but you're right, the shadow breaks.
That's because